and you just need maybe one more mark on 10 questions, and that's putting up maybe 1 or 2 grade boundaries.
If you had to give some physics tips on how to improve specifically the problem solving skills, what do you reckon the number one tip to do that?
Then this is a question I get asked a lot.
But
There we go, right.
Are you struggling to solve physics problems and then get 100%? Well, I'm kind of in the same boat. I've been struggling, so that's why I took the train to Bath and I've come over here to meet Lewis from Physics Online.
Hello, I struggle as well to get 100%, but we'll see what we can do here, I guess, to help each other, and yeah.
Let's see how to solve any physics problem. Well, here's a little physics problem over here. Classic one from OCR 2023, but applicable to all exam boards.
Yeah.
So what's the first thing that comes to mind when you come across a physics problem?
Normally, I see this and I kind of see the diagram, and I think the difficulty with that is it's not a diagram that's of a static object, and I'm sort of trying to imagine what that's trying to show. So we've got a fairground ride and it's rotating, so I'm trying to imagine that almost in 3 dimensions and think, okay, this is something that's moving. There's I guess there's going to be different forces acting that we don't see, because I guess all of these force arrows that we might draw, they're just like these things that we imagine. And I guess, yeah, there's also just a huge amount of information, and I can see already we've got at least 2 different distances and there's an angle. So my first thing is there's a massive diagram and there's lots of data, so I really need to kind of pay close attention when I actually, I guess, later in the question work out what I'm actually being asked.
Something which is very interesting that I've noticed with A-level physics problems is even if there's quite a lot of information, don't let that overwhelm you. For instance, if we look at the first one, and that happens a lot, it's just asking us to draw an arrow labeled T on the diagram to represent the tension, which is okay, and it's quite easy to be overwhelmed and think that this problem might be a little bit too difficult and to try and skip it. But if you ever feel like that, don't do this.
Okay, so I suppose the other thing I noticed there is that it's only 1 mark. So if it's a 1 mark question, it's generally not so much easy, but it shouldn't take too much in terms of having to apply equations and stuff. It should be a relatively straightforward first mark. So draw an arrow labelled T on the diagram to represent the tension in the rod. So I guess then we need to go back to the diagram. We can see we've got this rod here labelled there. And then I guess putting that into context, we've got a fairground ride, it's rotating, and each seat is suspended by a rod. So I guess I can imagine this being the kind of thing on like a fairly kind of ropey fair maybe, where you've got some like creaking things and it doesn't look safe, which I guess adds to the...
I'm just scared to go on those.
I guess it adds to the adrenaline rush that you feel when you're actually on something like this. So we need to think about the tension. Now, normally we think about tension being in a string or maybe a chain, but here we've got the tension in like a solid object. I guess if we've got a seat, which might have a sandbag on it, which I guess represents the person, there's going to be a weight force acting down initially, and that means the tension must be acting upwards in order to support them downwards. So immediately I know there's going to be, I guess, like an upwards arrow, but it's not going to be directly up because there's nothing there. So it must be within the rod. So I'd use my ruler, which I've lost. And also, if I was doing this in a real exam, I'd probably do it in pencil. I believe with OCR you can use pencil, but I'd also make sure I go over that maybe in my fine black pen at the end of the exam, so it's really clear. So using the ruler, we don't need to have a size in it, do we?
No, it's just an arrow.
So it's basically just which direction is it acting in. So from the seat, I'm going to do a straight line with my ruler. It's probably a bit overkill, but I think it's a good thing to do. I'm going to put my arrow pointing upwards, and then I'm just going to put T clearly on that, because I suspect some people might have forgotten to actually label that, so it was a bit unclear. So
that is a very, very typical mistake. Every time I used to mark mocks, usually I would mark at least a few marks down. You probably would have done the same if people just literally missing labels. Please don't do that.
And it's not that they don't know the physics. Like if you were to see them in class, you'd say, "Oh, what's that?" And they'd be like, "Oh, that's tension." But I guess in the exam, you're writing answers for some complete stranger who doesn't know you, and all they can do is say, well, if it's not labelled, I can't give can't give you the mark. So
another really common mistake, actually, just thinking about this, is completely missing out a draw or label question because there's no space underneath it. So it might be some people in the exam would have just gone straight to part 2, and particularly when you're under stress, this can happen. So just make sure to go logically in order. If you start off in A, make sure to go on to part B, etc. It's very easy to miss this. I know it sounds basic, but people lose marks every year on that. Okay, what type of command word have you got next?
Okay, so I like a show me question because when you've done it,
Me too.
you know you've got the marks. And basically, if you can get an answer that can then be approximated to 10, you've got a good indication that you're doing the right thing, which helps your confidence. And also, that's a clue for the next question. So if you're showing this is about 10, then I suspect on the next page there's going to be a question where we need to look at the radius of something moving, which I guess is also like the kind of thing you'd expect on like a circular motion kind of question. So my approach to this would be to start scribbling over the top of this diagram, or at least drawing neatly, because we need to show that the radius of the circular path followed by the sandbag is about 10. So I guess what we're thinking about really then is we're trying to work out this distance here, aren't we? Okay, so again, it's maybe not the neatest with this pen, but this is the radius r that we're trying to look at. And of course we aren't given that directly, but we are given enough data in the question, aren't we?
Yeah, we've got this distance over here, don't we? Which is not going to be quite 7.8 because 7.8 is the entire diameter, so we're going to need to halve that, but we can halve, it's fine.
Yeah, so again, a lot of the time they give you the diameter rather than the radius. So this is kind of like my centre line down here. And I'm just going to, this is like quite a rough diagram, but basically this smaller distance here is equal to half of that, which is 3.9. Hoping I've not made any simple mistakes. Okay, so we've got 3.9, and then we need to work out this distance here. So I'm just going to switch to green. And what I'm going to do is I'm going to label that as theta, I'm going to label that as h, that as a, and that as o. Now that is overkill. I'm sure if you're at the end of year 13, you know SOHCAHTOA, but if I do this, I'm less likely to make a mistake. And what I can see here is that the angle theta is 35, the hypotenuse in this case is 11.1 meters, and we want to know this side down here, the opposite side, because that's a right angle triangle. And therefore that's going to be our unknown. And then I guess I'm going to talk about Silly Old Harry. Is that yours?
Oh, I've never heard of that one, interestingly.
Silly Old Harry?
Yeah.
Couldn't afford his tired old alligator.
All right, no.
Okay.
I learned stuff, okay, perfect, yeah.
Yeah, I guess, how did you learn it when you were at school?
When I was at school, actually, because I went to school in Bulgaria and we didn't actually have an acronym.
Did you not have a Bulgarian equivalent?
No, we didn't. Yeah, very interesting.
Okay.
I learned SOHCAHTOA
Yeah.
almost immediately after, but yeah.
Well, okay, so we know that sine theta is equal to opposite over hypotenuse. So that opposite side is going to be equal to 11.1 times sine of 35. And maybe this is a bit over the top. I mean, I guess depending on what grade you're working at, but I know if I do this, there's no chance of me making a silly mistake. So 11.1 times sine of 35, and I think I'm in degrees, gives me an answer of 6.36. 36666. Okay, so that's going to be, this bit here is 6.367. I can see that this diagram isn't to scale because that's kind of double that, so it's obviously not to scale, which it does say as well. And therefore the total radius is going to be equal to this number. It's a lot quicker if you're just writing in black in the exam. And then we're going to multiply that, add 3.9 to that, which is equal to 10.3. Okay, but that's not my final answer.
Absolutely.
So what I'd always do is I'd work this out to at least one more significant figure than this number here, and that's going to be meters. And then I'm just going to do an approximate sign. That's approximately equal to 10 meters.
This will also really help your examiner because they will virtually immediately know. The only way we could have gotten that number to be 10.3 is to have actually done all the working out correctly. So I always make sure to include that.
Yeah, and I think that, although it obviously took a lot longer than 2 minutes to explain that, I just think that with a show me question, just be very clear about how you've approached that. You can scribble all over your diagram. You don't. I mean, if that's left pristine and unmarked, it's kind of pointless. And if you have too much onto it, it doesn't matter because you've already got your clear answer there that anybody's going to look at and go, you've got that right, and therefore that's correct and that's correct. They might have a quick scan there and just see, yeah, you're working out in your way. So, yeah, that's my first approach to that question, really.
Really good. So let's see what happens next. So what's the next one? We need to calculate the tension now. It's very, very typical that if we calculated the value, or it's very, very typical that if we've shown a value that we end up having to use it for a calculation. Shall we see if we actually need to use that? So we want to calculate the size. So I'm immediately starting to think about resolving the forces into their separate components. We've got the angle here, and it's a 3 marker, so we're probably going to expect a few more different calculations.
Yeah, I'd say that even though we've got something which is moving, it's still going to have things in equilibrium. So it just means there's no resultant force on it. And if we think about in the vertical direction especially, there's going to be a downwards force. Do you know, I'm just going to draw the diagram again. So I'm going to do that whole diagram like this. So that's going to be the seat with a sandbag on it. We've got a weight force acting down. So that's W. And there's going to be this tension in that rod. So I'm just going to consider this bit over here. So this is going to be the tension force in the rod. That's it. They're the only 2 forces acting on it, aren't they?
Yep.
So we've got a weight down and then tension up and to the side. And in the vertical direction, the seat isn't moving up and down as it's going around. It's just staying at the same height, at the same level. So what we can then think about, I guess, is also maybe just adding. I'm just going to put a dotted line here.
Perfect.
Or it could be, it doesn't really matter if it's dotted or not, does it? And I'm going to label that as 35 degrees. Okay, so that's basically information. That's all the information I need from that whole diagram. And that can just go off to one side, I guess. And yeah. Calculate the tension in the rod. Oh, actually, I need it back. So, because we need to look at the size of the weight force down.
Yep, indeed.
And we've been given the mass. So, I might just write out an equation that says the weight down is going to be equal to the mass times gravitational field strength. And that downwards force is going to be equal to the component of tension in the vertical direction, which I'm going to call, let's say that's equal to TV. So tension vertical. But I think anybody reading that would be quite clear what that is. And that's going to be equal to T times something of 35. Okay, so it's either going to be sine or it's going to be cos. But I guess we've got like a closed angle there, so this is going to be cos. So I guess that's maybe one way I've sort of learned about if that's,
that's
like
really
closed.
interesting.
It's like that's the closed angle. So that's going to be T cos theta, and that one there would be T sine theta. So basically, because we can equate this and this together, we can say that mg is equal to T cos 35.
So now we're in business because we know what m is, we know what g is. We're looking for t, and our trusty calculator will be able to give us cos of 35.
Yeah, so I always rearrange, then put the numbers in. So
I always do exactly the same.
Sometimes people, I think at GCSE it's a bit like you put the numbers in, then you rearrange, but I just think it's better to say that t is going to be equal to mg divided by cos 35. And then I put, I suppose I probably could have put theta there really, but that's going to be equal to 12 times 9.81 divided by cos 35. Okay, so you're going to your calculator.
There we go, 143.7.
So that's equal to 143.71. Now, that's not my final answer. That's too many significant figures. And I guess looking back at the question, I'd then be thinking, well, we've got the... What have we got? We've got the angle is 2 significant figures, and the mass is 2 significant figures. So I'd give that to 2 significant figures. And the best way to do this would be in standard form of 1.4 times 10 to the 2 newtons.
And that's this problem sorted.
Is that the right answer?
It is, I'm pretty sure. Let's see.
Yeah, let's just check in case we've made a mistake. But yeah, I think 140, yeah, I think 140 is fine. Yeah.
It also makes sense. We've not gotten 1,000 newtons. We've also not gotten 0.001 newtons. So it's always really, really useful to have a little sanity check. If you're calculating the mass of a galaxy and if you get a couple of kilograms, you probably need to go back and change it. But this answer makes perfect sense.
Cool.
We've got another show question. This one is about the angular velocity. And we want to show that it's about 0.8 radians per second. A few different ways of approaching this, because there's multiple different equations that we could use both in circular motion and for what angular velocity actually is. So how do you approach this one?
Okay, I guess this one, to me, looking at it, I feel that there's kind of more work to do for this question than that one. That's like 3 marks and that's only 2 marks.
I would agree.
So I would have thought, okay, is there a simple way to do it? But I can't see like a super simple way. But I would think, okay, so we're now thinking about angular velocity. So there's equations that we can think about. So we've got F equals mv squared over r. That's one of them. But this is talking about angular velocity. And therefore we can also think about how force is equal to m omega squared r. Or is it mr omega squared?
Yeah,
I can't remember which way OCR has it round, but these two are both the same thing basically. And because we're looking at angular velocity, I'd probably go for this one. So
I would do the same.
Yeah, so then it means, do we know the mass? Yes, we do. We know the radius because we had to look at it over here. So we already can use a value for the radius of 10 or 10.3. So I'm going to use my calculated value rather than the 10 figure, because that's a better value, I think, using the data. So we know this, and we know we can work out the force. So we know that there's a force here that's acting at an angle, and there's going to be a certain horizontal component of that force. Before we said this was TV, so this is going to be TH. So that's the component of tension in the horizontal direction, and that's going to be providing the centripetal force. So this TH is going to be equal to m omega squared r, and we want to find omega, don't we? So then I'm going to rearrange all of this to say that omega squared, I'll do this first, is equal to TH, which is going to be, that's an angle theta that we've been given. So that's going to be equal to T sine theta divided by mr. And then it's going to continue it up here to say that omega is going to be the square root of T sine theta over mr.
One of the advantages of what Lewis is doing, just to kind of provide a little bit of commentary, is that while he's doing that, he's not calculating multiple different things, inputting four or five different things into the calculator, but he's got an expression that he's going to input right at the end, and you're far less likely to do a mistake if you try and minimize calculator operations, in my experience. Several small exceptions do exist, but these are relatively rare.
Yeah, I realise I'm kind of sort of done awfully in my use of space, but basically this is where I've got to. So we've got the value of t that's calculated, not the rounded down value. We've got sine 35, because if that was cos 35, this must be sine 35 for this. And then we've got 12 times 10.3, which is what I calculated over here. And I think when we do all of that, we can then work out a value for omega. And I'm going to probably write down the calculated value on the calculator, just in case we need it later on in another part of the question. But also this shows that I've gone through all of the steps.
Yeah, 0.81.
Okay, so that's 0.8166, so 0.817, which is 0.81. And here, interestingly enough, they haven't... Oh yeah, we've got the answer we're trying to find, 0.8. So I'm going to give this a 0.81 radians per second, which is approximately equal to 0.8. And I guess this last step here shows I'm kind of relating this back to that. Okay, now that is not particularly messy. Oh, sorry, it is particularly messy, but I think that somebody following this could sort of see what's going on. And I'm maybe just going to underline my answer just to make it clear that amongst all of that mess, there is the right bit of physics.
I think it's also really important that every time you write an expression, you're writing an equal sign right next to it. The number of times when I've been marking and I've come across just sort of t sine theta written here, and then maybe just 143.7 times sine of 35 written on the other side of the page. And I get it, because you're trying to think, you're scribbling, but the scribbling is best done either near the diagram or in a different part, and try and keep your work really, really logical, starting from an equation and then finishing at your final result in a show question. Okay, part B, let's have a look. So when the seat is at its highest point, the sandbag is 17 meters above the ground. Can immediately just, I can feel the SUVAT question coming. The sandbag is released from the seat, there we go, and we want to calculate the time taken for the sandbag to reach the ground. Okay, so this here is a question which is almost hidden within a question. That's one of the things that you definitely need to be ready when you're doing A-level physics. Especially these days, it's increasingly rare to have an entire question just on one topic. Different bits of topics, especially if your year 2 parts of year 1 are going to appear within a wider question, and this is one of those parts. So, good old SUVAT. How do you approach SUVAT?
Okay, I like SUVAT because it's covered in year 12. It's covered in maths in year 12. You might have seen it at GCSE perhaps before, if you did maybe like some advanced maths when you did GCSE level. And again, you've been using it in year 13 when you've looked at particle motion in like electric fields. So SUVAT should be like guaranteed marks. But I would still say I'm going to write down SUVAT.
We should check out the examiner's report afterwards, actually, to see
how
guaranteed it was.
We do. Well, yeah, we've got the examiner's report here. We'll see how many people got this correct. Yeah. But I'm going to do SUVAT just in the vertical direction, because what we have is, I guess, something where something is released at an initial horizontal velocity, and then it's going to follow this parabolic path down to the ground. But I only care at this time about the vertical component of that. And in the vertical direction, I'm going to say downwards is positive. Okay. Because
the direction of motion is downwards in this case, so that makes total sense to me.
So the distance is 17 meters. The initial vertical component of velocity is 0.
That's really high, by the way.
17 meters. I mean, if you're on one of those,
six-story building or something like that.
I don't know, but also I guess that thing's like 11.1 meters. So this is going to be an amazingly massive, creaky structure. Okay, we don't know the final velocity. We know the acceleration is 9.81 meters per second squared, and we don't know the time. So we've got to think about something that doesn't have a v in it, which would be s equals ut plus a half at squared. And I already know what I'm going to say next. So s is equal to ut plus a half at squared. And as is always the case, I'd say, ut goes to 0 because u is 0. So it takes this SUVAT equation and it makes it just s equals half at squared. And then we can rearrange this to make t the subject. So t squared would be equal to 2s over a. So t is going to be the square root of 2s over a. I've kind of done that in one step. I'd probably do that in the exam. I wouldn't write down all my intermediate things. And therefore, the time it takes is going to be 2 times 17 divided by 9.81 square rooted. Is that what you've been working out?
I think so, yeah. So let's see, so around 1.86 makes sense in terms of the amount of time that you would expect.
I imagine if you fell off a roller coaster or like a merry-go-round, thing like this, if you fell from 17 meters, you'd have at least 1.86 seconds of sheer panic in the air as you felt yourself dropping. So I reckon it definitely wouldn't be 18 seconds, and it definitely wouldn't be 0.18. So I think 1.86 seconds is appropriate. And so my answer down here would be 1.9 seconds.
Let's see if I can put stuff into a calculator.
Okay, let's have a look. I always find it weird when you've got like an answer line with the unit over here that you don't necessarily have to put the units down. So yeah, 1.9 would be my answer. Yeah, it does say 1.9 seconds is the correct answer.
Yep, perfect.
So I guess if I've got that, I'm probably going to get 2 marks anyway. But I can definitely see a mark for like using the right equation and substituting stuff in. Okay.
Very well done. Okay, now this is this is essentially a projectile motion question, which is hidden within the other questions. So what do we got? We want to determine the horizontal displacement traveled by the sandbag before hitting the ground. Now, we're obviously assuming something though, which is not incredibly realistic, I imagine, for this problem, which we might talk about later. But this will only be true in the absence of air resistance. So,
yeah, and I guess we assume that for the first bit. So we assume that there's no air resistance. So we have a uniform acceleration of 9.81, which got us to this. Can I draw a diagram?
Yeah, of course.
There we go.
You do
That
like a
is
diagram?
basically, that is the motion. So this is, it was a shoe, wasn't it?
Yeah.
Okay, the sandbag was released. So this is where it starts. And there's going to be a certain amount of time that it's falling for. And during that time, it's going to be travelling horizontally. So here, we need to think about two things. There's going to be the velocity it was initially travelling at. I mean, sometimes I write down SUVAT, but it's not really, basically this is acceleration is 0. So let's say there's a velocity of this sandbag as it's dropped, and we know that it's falling for a certain time of t. And what we want to do is work out this displacement. Well, it's a bit messy, but that's S. So basically, this is an equation that's not in the data book because it's just speed equals distance over time.
Absolutely.
So distance is going to be equal to this horizontal speed times the time which it was falling for.
So we need to figure out the horizontal speed. Now, how can we figure out the horizontal speed? And this is where we have to really imagine what's happening, because as you mentioned in the beginning, there was a merry-go-round with something which was moving in a circle, and we already talked about the angular velocity, so perhaps we could just blend some of the equations from year 2 and year 1 and think about v being equal to omega r.
Yeah, so this horizontal velocity then, or the instantaneous speed at the edge of this rotation, is going to be equal to r omega, or omega r. I like r omega more.
Interesting.
Now, if I guess we can just put this straight back into there to say that S is going to be equal to r omega t. And then we can just put the numbers in. Now, we need to know the radius, which is what we worked out in part A2, which it says 10 meters, but I worked that out as 10.3.
If you didn't know how to show this, would you have a scan in the question, see if you can use that value in any of the other bits?
That's right. And I think even if I didn't get this, I could just default to the given value of 10. And also, it does say to use your answer from A part 4, which is 0.8, but obviously we worked that out as 0.817. So I'm going to use 0.817. I'm going to multiply that by this time of 1.86. Now, of course, if I just did 10 times 0.8 times 1.86, I'd also get all the marks, because it just shows I'm using the right method even if I'd messed up part A. So what have we got? We've got 15.65. So I'm going to say to two significant figures, because that's all we can really, because we've got two significant figures there, is going to be 16 meters. So yeah, basically, if the sandbag fell out at 17 meters high, it would also go 16 meters, which is quite a long way.
It is a very long way. So I'm too concerned about safety to go on one of those. Right, this is where the question takes a massive twist. It's a very, very creative question. Massive props to the person who made this question, whoever you are, if you're watching this. But
there we go, right. There's a shoe.
This was totally planned.
Sorry about the smell. This is, it's been worn all day. Right, okay.
I gotta go back to Manchester.
Right.
Determine with reasons the effect on the horizontal displacement travelled if the object released from the ride was a shoe from a rider. Okay, now determine with reasons. So notice the command word. It's determined. Things like suggest or determine with a reason probably tells us that we might have a little bit more freedom. The thing to do here is to think what reasons, which are grounded in physics, hopefully because we're doing a physics exam, will really make a difference for this. You can also look back and see if you've missed anything from those calculations. For instance, drag was definitely missed. I would definitely write this. For instance, the connection between mass and motion and projectile motion could be something else that you could be considered. Likely, most of these things will appear in the mass scheme. We hope.
So, I don't know the exact answer in real life if it would make it go further or less distance, and the reason for that is that if you've got the seat here. And before we had the sandbag kind of modelled like that, and we know that this that's going to run out. We know that the distance of that rod was 11.1 metres at an angle of 35. Now, of course, when there's a person on it,
it's longer, isn't it?
Yeah, so their centre of mass isn't going to be here. It's going to be out here, maybe. Now, just thinking about how long my legs are from like my centre of mass, it's like maybe when I'm sat down, I don't know, maybe 0.7 of a metre. So really what we need to do is we need to add another 0.7. Now what that means, it's got two effects. First of all, the distance from the ground is going to be less than it was before. So maybe that was the initial height. So we can see that it's closer to the ground, which means it's going to be falling for less time. So if it's falling for less time, it's going to hit the ground quicker, provided there still wasn't any air resistance. But if we think about the radius of it, well, before the radius might be this much. Oh, that's the awful horizontal line. Whereas now, the radius is going to be bigger. And so what I would say is that the value for t is going to be smaller, but the value for the radius of its movement is going to be bigger. And on the last equation, we said that the horizontal displacement is going to be equal to r omega t. Omega is going to be the same. So omega is going to be the same value. But what we now have is a bigger r value and a smaller t value, which would then give our value of s. So it's not a clear-cut thing of it's going to be definitely smaller because the time is smaller. We could say that this could be bigger because r is bigger. And it's which of those has the biggest effect. And I suspect you could probably work this out by, actually working out the new height it fell through and also the new radius based just on like an approximate 0.7 thing in difference. But what we don't have in those calculations is the effect of air resistance,
Absolutely.
Which is like a non-linear kind of thing anyway.
And it depends on so many factors. I mean, if the show of the rider is significantly lighter than the sandbag, which I imagine it is the case, they're going to have very different terminal velocities. Mm-hmm. They're going to react to drag potentially very, very differently.
And obviously heavier objects fall faster. Oh no, I mean, they're going to have definitely different terminal velocity depending on so many different factors. And is it a croc or is it going to be like, like a Doc Marten boot or something? However, you don't want to overcomplicate this. I suspect you could probably have a whole debate on this and come up with lots of different things. I'm
going to put the mass scheme. It's going to magically appear around us here somewhere. So have a look at this mass scheme. Hopefully what we've been talking about is accepted onto there.
Yeah, but I think as long as you're backing it up. So you might say, I don't think it will travel as far because it spends less time falling in the air because it's closer to the ground. So if t is smaller, then it won't travel as far horizontally because it's travelling for less time. And I think as long as you can kind of take an answer, and bear in mind, this is just an exam. You've only got, 3 minutes to consider this and write it down. You don't want to think too deeply. And you've got to realise that as long as you can kind of back it up with some physics, and it's, the reasons, then I think as long as you can relate that to the kind of stuff you've already done, you can get the marks from that. You don't have to overthink and overanalyse.
And if you had to give some physics tips on how to improve specifically the problem-solving skills, what do you reckon the number one tip to do that would be for our audience? I
think, and this is a question I get asked a lot, and there's no simple answer. Mainly, if you just do more problems, you'll just get more used to seeing the different language, the different questions that can be asked. The more problems you do, the more used you'll be to actually going through mark schemes. So if you did twice as many problems as somebody else, you'd be exposed to twice as many mark schemes, twice as many examiner reports, and you just spend just more time actually doing that thing. There's no shortcut really. I mean, there's not one thing that you can do that's going to give you an extra 20 marks each paper, but generally the more problems you do, and then the more time you spend actually analysing maybe where you made mistakes, the better you're going to become in your general kind of physics practice. And
I couldn't agree more.
And it's just you might do this the first time and realise that you've missed the word draw. But then, of course, if you then know you did that mistake in this paper, the next time you see a question where you've got to draw on an arrow, you're going to be much more likely to think, oh, I made that mistake previously, I've learned from that. And then these little 1 and 2 marks here and there across the whole paper can really add up over many questions. I mean, this is question 17, and you just need maybe 1 more mark on 10 questions, and that's putting up maybe 1 or 2 grade boundaries.
Side note, but if they've solved like all the past papers from their exam boards and they need to get a book which has some extra questions, what could they possibly look at?
Okay, so I've got a load of stuff I've done, but first of all, just actually double check you've actually done all the past papers from your exam board, because sometimes you realise if you haven't been keeping on track of what you've been doing, that, oh yeah, there's the 2019 papers, I forgot about those. So first of all, just keep on track of what you're doing. There are papers from other exam boards which are going to be similar.
Yeah. The legacy papers are quite good as well.
Yeah, there's legacy papers. These are a bit more difficult to find sometimes, but a question from 2008 about circular motion could be identical to this pretty much. Maybe slightly different numbers, but this is not a new style question. This is just a standard physics problem. I've written some practice papers which have got questions in for like the kind of practical topics. You've got question packs by topics. PMT on their website, they've got question packs that they've just taken from the different exam boards and just like done on different topics. I've got a daily workout book with lots of questions. And also, I think there's stuff like Isaac Physics, which is brilliant. So there is no excuse for not having access to questions. What you need to do is actually just sit down and do some of them. And whatever it is, stick to it and just do as much as you can. And that's going to really just help you progress in your physics.
Lewis, thank you so much.
My pleasure.
And thank you so much for hosting me and being on Z Physics. And this was not the only video that we've done. We've also done yet another one which we covered a really, really interesting problem. So you should definitely click on this video that I'm going to leave somewhere right over here on Lewis's channel. Make sure to subscribe to both of us and click over here.